This is the second of our four-part series of video examples addressing application of alkalinity concepts. In this video example, we'll calculate the alkalinity of the pristine rainwater we examined in the first video of this series. We characterized that pristine rainwater, and now we'll use that characterization to amplify upon the example 3.4 of Water Quality Treatment, 6th edition. We'll first visit the concepts behind alkalinity, examine the specific laboratory test that carries the alkalinity name, and along the way we'll correct a minor but important error from the general literature in the general interpretation of alkalinity test. Our computations will be very specific to the pristine rainwater of part 1 of this series, but the overall approach will be widely applicable. Alkalinity, the test, is of course the measurement and reporting of the number of hydrogen ions, sometimes we call them hydronium, sometimes we call them protons, that are assimilated when an aqueous solution is titrated using a strong acid from its initial pH to a pH endpoint of about 4.3. Most titrations these days are done using a pH meter to sense the endpoint. Early lab work, of course, used colorimetric indicators. Methyl orange turns from yellow to orange in the pH range of 4.4 to 4. Brome cresol green turns from green to yellow in that pH range of 4.4 to 4. If we were to use these indicators in a titration of rainwater, since they are themselves bases and would accept protons, they would impart a positive bias to the result. So were we to titrate rainwater for the alkalinity test, we'd do it entirely potentiometrically. And of course, the 4.3 pH endpoint ensures that virtually all of the carbonate initially existing and all of the bicarbonate initially existing in the aqueous solution are converted to carbonic acid. And from the carbonate system equilibria, if we use a pH of 4.3 with the K1 value, we find that at pH 4.3, the ratio of bicarbonate to carbonic acid is about 1 to 100. 1%. Then also at pH 4.3, H plus squared is 10 to the minus 8.6, we find that the ratio of carbonate to carbonic acid is about 1 to 10 to the 8th. Very, very, very insignificant. As we mentioned, alkalinity is a measured parameter. We titrate a water sample from its initial pH to pH 4.3 using a strong acid. We measure the acid consumed. During that titration, we have hydroxide accepting protons to form water. We have carbonate accepting protons to form bicarbonate. We have bicarbonate, both that initially existing and that created by the conversion of carbonate, accepting protons to form carbonic acid. And we have water accepting protons to form hydronium ions. So let's examine those changes in the carbonate and water species concentrations that result from the addition of that strong acid. We have 1 mole of protons per mole accepted by each mole of hydroxide converted to water. We have 2 moles of protons accepted by each mole of carbonate to convert it to carbonic acid. We have 1 mole of protons accepted by each mole of bicarbonate as it's converted to carbonic acid. And we have 1 mole of protons accepted by each mole of water converted to hydronium. So the change in the alkalinity of the water sample as a consequence of the titration has to equal the change in hydroxide concentration plus twice the change of the carbonate concentration plus the change of the bicarbonate concentration plus the change of the water concentration. Summed together, these are algebraically the negative of the sum of the protons added through the acid addition. Of course, we can't measure the change in the water concentration, but fortunately we can equate the change in the water concentration to the negative of the change in the hydronium concentration. We can rewrite our equation, substituting the change in the hydronium concentration, the negative of that, for the change in the water concentration. We flesh out all of our changes as the final value minus the initial value for alkalinity, for hydroxide, for carbonate, for bicarbonate, and for hydronium. Here we have the equation where we've summed all of those fleshed out changes as it would appear in a MathCAD worksheet. We know that the final alkalinity needs to be 0 relative to the pH 4.3 endpoint. We know that the final bicarbonate and carbonate concentrations are 0. We know that the final hydroxide concentration is very, very small, and we can consider that to be 0. So we use MathCAD 15 to make the final calculation. We assign all of our initial values into a 4-row, 1-column matrix containing the initial values. We assign our final values into another 4-row by 1-column matrix for the final values. And of course, the initial values are from the pristine rainwater pH calculation from part 1 of this series of videos for 1 atmosphere total pressure, carbon dioxide concentration of 395.8 parts per million by volume. We've taken the previously stated equation and we've multiplied both sides by -1 to dispense with that negative sign on the initial alkalinity. And of course, now the right-hand side is all now the initial values minus the final values. We see that the result is 5.01 times 10 to the -5th moles per liter. We can convert that, as we should, for comparison, to milligrams per liter as calcium carbonate. We have our conversion factor that 50,000 milligrams per liter as calcium carbonate is 1 equivalent per liter. And so our final alkalinity that we would report would be 2.5 milligrams per liter as calcium carbonate. Now we compare this with a very small negative value that's computed in example 3.4 of Water Quality and Treatment 6th edition based on their equation 351. And they, of course, suggest that that small negative value is 0. So let's see what a revised version of equation 351 of Water Quality and Treatment 6th edition would look like. The only difference is here we've added the final hydrogen ion concentration to the right-hand side of the equation. Then for water samples with high inorganic carbon content, when we neglect these last 3 terms, we impart very insignificant error. Conversely, if we have low inorganic carbon content, if we neglect the final hydrogen ion concentration, we can impart significant error. And also for low inorganic carbon content and low initial pH, if we neglect the initial hydrogen ion concentration of the water, we can also impart significant error. For water samples with low inorganic carbon content and high initial pH, of course this is unlikely for natural waters. If we neglect the hydroxide ion, we can impart significant error.